Hi guys! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. At ang ating magiging topic for today is all about economic section. At sa pamamagitan nitong video na ito ay ipakikita natin kung paano gumamit o mag-design ng isang beam sa pamamagitan ng paggamit ng most economic section. So guys, puntahan natin muna itong ating introductory discussion. Okay? Kung babalikan natin yung ating flexure formula, okay, that gives the relationship between the stress and the bending moment that causes that stress. Ito yung ating makikita, di ba? Ito yung formula na ginagamit natin, that the stress is equal to MC over I. Na kung saan yung M dito ay yung bending moment, yung I ay yun yung kanyang moments of inertia ng beam cross section about the neutral axis, at yung C naman dito yung location of the fiber from the neutral axis, okay, na kung saan yung stress ay kinukuha natin. At maobserbahan natin dito na yung ating stress is directly proportional to the location of that fiber. Sa makatwid, okay, kung yung fiber ay closer sa neutral axis, they will be subjected to lesser stress. In other words, they will be considered as under stress. Kung ikukumpara natin yan dun sa mga fibers that are located farther from the neutral axis, kasi they will be subjected to a larger stress. Sa makatwid, for those beams that consist of larger portion of under stress fibers, gaya halimbawa ng rectangular section o kaya circular beam, they become less efficient in resisting flexural stress. So nagiging mas inefficient sila in resisting load because they will be subjected to lesser stress. So in order for the beam to be more efficient in resisting moment, okay, if we're going to go back to this formula that we have for the stress, and then we rearrange this formula and solve for the M. So magkaroon tayo ng formula that M is equal to the stress multiplied by I divided by C, or simply it will be equal to stress multiplied by the ratio of I over C. Ngayon, kung obserbahan natin itong formula na ito, so mapapansin natin that the moment capacity, ito yung moment capacity, for a section given, okay, the allowable stress will be greater if for the same depth, kung halimbawa daw hindi naman mababago yung kanyang depth, the section will be rearranged so that its moment of inertia will be greater or will be increased. Mas magiging malaki daw yung kanyang moment capacity, okay, kahit hindi na mabago yung kanyang depth. Kung i-rearrange natin siya sa pamamagitan ng pagdadala, okay, pag-i-increase ng kanyang moments of inertia about the neutral axis. And this can be attained by placing more fibers farther from the neutral axis. Kung magagawa daw natin na yung ilang fibers ay mailalayo natin mula sa neutral axis, then we shall be able to increase the moments of inertia, and therefore the moment capacity of that section for a given allowable stress, and considering that the depth will not be changed, it will be increased because I will be increased. So halimbawa, ipakita natin, kunwari meron tayo ditong section, okay, rectangular section. Mapapansin natin na yung mga fibers na nasa dulo, okay, yung mga fibers dito o kaya dito are subjected to larger stress. Samantalang yung mga fibers that are closer to the neutral axis, somewhere here, yung mga fibers na rin dito, ay lesser ang kanilang stress. Ibig sabihin, they will be under stress. What if those fibers that are located closer to the neutral axis shall be placed on a position farther from the neutral axis? Gaya halimbawa na ipapakita ko sa inyo, kunwari, itong section na ito ay ginawa natin ganyan, that there are fibers that are removed from the neutral axis, from the position closer to the neutral axis and placed farther. So what will happen? Okay, their moments of inertia will be increased. And for the same depth of this section, okay, it will have therefore a larger moment capacity. At ito nga yung ginagawa, okay, sa mga metal beams that are made up of steel or kaya aluminums. They are rolled in the form of an I section para mas maraming fiber ang nailulocate farther from the neutral axis, and with this section, okay, they are able to resist more loads. At ang ganitong klaseng section, ito yung tinatawag nating economical section. Marami siyang section, meron siyang ganaring klase ng section. Okay, pero ang most common section na ginagamit sa industry, ito tinatawag nating wide-flange section. O kaya binibigyan siya ng designation na W shape. So itong tinatawag nating wide-flange section or W shape ay very very common na ginagamit natin sa industry. Bakit siya tinawag na wide-flange section? Kasi itong flanges, okay, itong dalawang flanges na ito, okay, ang kanyang width ay mas higit na mas malapad. Yung B sub F niya or yung kanyang flange width is comparably larger. Ba? Kaya we call this as the wide flange. And this section are designed so that meron siyang tinatawag na web that will keep these flanges in their respective position. And this web has a certain thickness called T sub W. Okay? So, ang isang section pa na ginagamit natin ay ito namang tinatawag nating I section. Okay, I-beam. Okay, o yung tinatawag nating S-shape. So, bakit sinabing I-beam? Kasi medyo mas maliit na ngayon yung width ng kanyang flanges at it actually looks like letter I. Kaya tinawag siyang I-beam. So, in other words, they are called S-shape. Diba? And they are most common in the industry. The other section na makikita natin sa industry, yung tinatawag nating angular section o kaya channel section. And they are also used, kaya lamang most common in particularly in the beam or structural elements that are subjected to bending moment. The most common are the wide flange section o kaya the I-beam. Ngayon, paano natin siya i-designate? Paano siya ipinakikilala? Ang ganda rin klase ng mga section. Halimbawa, meron tayong wide flange section o yung tinatawag nating W shape. Ang ganda rin klase ng wide flange section ay i-designate sa magitan ng ganda rin klase ng notation. Meron tayong W, then you have the first number or N sub 1 by N sub 2. Na kung saan itong W na ito tumutukoy sa kanyang type, that this refer to a section having flanges that are wide enough. Kaya siya tinatawag na wide flange section. Samantalang itong N1 naman, it gives the approximate depth of the beam. Kumbaga, ang kanyang depth, itong taas niya mula dito hanggang dito, ay makikita mula sa first number that designates the section. The first number here, N sub 1, gives us the approximate depth of the beam. While N sub 2 here gives the theoretical mass of the beam. Kung gaano naman siya kabigat, yung kanyang mass given in terms of kilogram per meter kapag ang ating section ay in SI. Kung siya naman ay in English, it will be given in terms of pound per inch or pound per linear foot. Depende kung anong manufacturer ang nagpo-provide ng ganyang klase ng section. Kaya kung halimbawa meron tayo dito ang ganitong klase ng designation, W460 by 97. Ang ibig sabihin nito, we have a wide flange section, diba? Or W shape na kung saan ang kanyang approximate depth ay 460 mm. Yung taas nito, ay about 460 mm. And it has a mass that is equivalent to 97 kg per linear meter. Bawat isang metrong haba na ring klase ng section na ito, itong section na ito, ay mayroong mass na 97 kg. While for the other section naman, okay, for I-beam, itong ganang klase ng section na kung saan, okay, yung kanyang flanges ay shorter, ano? Okay, we call this as an S shape. Ito i-designate sa pamagitan ng symbol S. Then we have a pair of number also. We have N1 and sub 2. And again, S would refer to the shape. It okay, actually is referring to an S shape or an I-beam. Ba? And the first number also gives us the approximate depth of the beam. And the second number gives also the theoretical mass of the beam in kilogram per meter. Kaya kung meron tayo halimbawa na isang S-section designated as S 180 by 30. Ang ibig sabihin nito, you have an I-beam or S-shape na ang kanyang approximate depth ay 180 mm and a mass of 30 kg per meter. At pag sinabi nating economic section, dahil ang mga materials natin ay binibili by the weight or by the mass. Therefore, ang ginagamit natin is the lightest. Kung aling section ay may pinakamagaan na section, yun ang ginagamit natin as equivalent to the most economical. Because if you are providing the lightest section, yung pinakamagaan, it can be purchased using the minimum cost, and therefore you will have the most economical section. Di ba? Now, paano ito ginagamit? Okay, kinakailangan maunawaan muna natin kung ano yung mga properties ng built-up section. Ano ba itong property nito at saan matatagpuan ang mga property ng ganaring klase ng built-up section? So, ipakita natin, kalimitan, kung ikaw ay may libro ng Strength of Materials authored by Ferdinand Singer, okay, the properties of this kind of section, itong wide-flange section, itong S-section, yung channel section, yung angular, can be found as Appendix B of that book. Okay, this book, Strength of Materials, authored by Ferdinand Singer. And I will show you para makita ninyo, maging familiar kayo paano siya gamitin. And here is the explanation, the book. So, the book actually is the Strength of Materials. Normally, kahit ano, pero yung 4th edition niya, meron siyang SI at meron siyang English property. Kaya if you are designing using an SI unit, so you can use this table, the table that can be found here in designing the most economical. Or if you are using an English system of unit, so you can also use this. Okay, so where we can find that property, this can be found as Appendix B dun sa huling bahagi, and I will show you. Kung bubuksan mo yan sa huling bahagi ng libro, somewhere at the back, you can find the Appendix B. Medyo may ilang pages siya that will show the property, the property. So you will have the property of the W-flange, wide flange. You will also see the property of the S section. You will also see the property of the channel, the angular, and so on and so forth. Now, paano siya gamitin? Mapapansin natin, this contains the different numbers, different numbers. And to understand this table, here is how we are going to do it. Okay? So, ipakita ko yung, medyo palinawan ko lang. Kumuha tayo ng isang particular page kung saan ipapaliwanag natin yung content niyang table na ito. Ito yung content. So, ganito natin makikita yung content ng table. Okay? Yung content ng table. Okay, the table have the following columns. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 columns. For, the properties of wide-flange section, SI unit. Kaya, kung SI ka, so you can find for this property. Okay? Now, puntahan natin yung kanyang column. Yung column 1, tumutukoy dito. Yun yung kanyang mga designation. And that designation gives the approximate depth and mass of the section. Kaya kung kukuha tayo halimbawa, itong tinutukoy natin nasa unang bahagi, 460 by 177. So, maliwanag na itong section na ito, ang approximate depth niya ay 460 mm and it has a mass of 177 kilogram per linear meter. And you will find that there are several sections having different mass for approximate the same depth of Okay, halimbawa 530 by a series of numbers. Sabihin, this group of sections have almost the same depth of 530 and they vary. Okay, they vary in terms of their masses. Masses ranging from 66 to 219 kilogram per linear meter. Di ba? So makapamimili ka diyan kung ano yung most efficient and most economical. Now, yung second column is the theoretical mass. Ito yung theoretical mass na tinutukoy natin. Okay? It gives the approximate. Kung mapapasin natin, kung meron tayong 66, this representing the approximate mass, ang actual mass niya is 65.7 kilogram per linear meter. Kung meron kang 101, yun ay 101.4. So at least meron ka ngayong idea, di ba? Now, puntahan natin yung column 3. Yung column 3 is for the area. Itong column 3 representing the area. This gives the total area of the built-up section expressed in millimeter square. Yung section na ito, yung kabuuang section na yan, gives that area. Okay? And that can be found on column 3 of that table. Yung next column, column 4 is the depth. Ito yung depth na tinutukoy natin. Diba? At mapapasin natin, kung meron tayong approximate depth na 130, yung actual depth niya is 560. At least hindi malayo doon sa 530. Ano? Yung 530, mapapasin niyo that they are almost very, very close to that. And they are grouped as to have almost the same depth of 530. Okay? Yung next natin is the flange width. You will notice that the next two columns is for the property of the flange, na kung saan itong part nito will represent the flange width. Itong haba, itong lapad nito, yun yung tinutukoy niyan. Ano? So kung meron tayong 165 dito, itong 165, ibig sabihin ito, itong kanyang width nito is 165. And then the next column, is the flange thickness. Ito yung part nito, flange thickness. Puntahan natin, kung meron akong halimbawang 11.4 dito, representing the flange thickness of a W530 by 66. Ang ibig sabihin, ito yung thickness nito mula dyan hanggang dito. Yun yung thickness ng flange. Okay? Then the next column is the web thickness. Itong part nito. Okay, the web thickness representing this column. At yan ay tumutukoy dito sa thickness itong web na ito. Okay? Then you have the next column. The next three column, Next three column for the column 8, column 9, and column 10. It actually gives the property of the section kapag yung section natin ay ginamit such that the x-x axis is the neutral axis. So, anong ibig sabihin ito? Kung titinan natin yung ating section, meron tayo kasi illustration somewhere here sa itaas nito, na kung saan ipakikita alin ba yung x-x axis. Ang x-x axis na tinutukoy dito, itong axis na matatagpuan natin dito, yan. Ibig sabihin ito, kapag ang orientation ng ating section is in the form of this one, na kung saan itong x-x axis natin ang nagsisilbing neutral axis. Sa makatuwid, ang property ng section na gagamitin natin is the column 8, column 9, and column 10. Diba? Na kung saan yung column 8 natin, yun yung kanyang moments of inertia with respect to this axis of the entire section. Itong entire section na ito. Diba? And ito namang next column, column 9, gives us the modulus, section modulus. Ito yung tinatawag natin section modulus na kung saan ang kanyang definition is the ratio of I over C. Kaya kung kanina nakita natin yung I over C doon sa earlier presentation ko ng formula, nagkaroon tayo ng ratio ng I over C. Actually, ang tawag doon is section modulus na kung saan ito yung kanyang section modulus expressed in terms of times 10 cube millimeter cube. At ito very very important itong column nito kasi dito tayo magbabase kung paano siya gagamitin, kung aling section ang pwede nating piliin sa pag-define, pag-decide which economical section are we going to use. Okay? Yung next section natin is the radius of gyration of this section kapag ginamit natin to in this axis. And this particular section, very, very useful siya kapag ito ginamit natin as a compression material or compression materials as a support to resist compressive loads. Halimbawa, poste, ginamit siya natin as poste. Okay, itong part nito, itong property nito, the radius of gyration, will be very, very important. Then the next three columns, 11, 12, 13, representing this. 11, 12, 13, ito naman yung property ng section, the same section, kapag ang section natin ay ginamit natin such that the YY is the neutral axis of the beam. Ano ibig sabihin itong the YY is the neutral axis of the beam? Kapag itong section natin ay pinihit natin at ganito ang ginawa natin, ibig sabihin the section of the beam, ganyan natin nilatag that this is our neutral axis representing the YY axis. Ang ibig sabihin yan, ang property na gagamitin natin are these three properties. And these three properties gives us the following. Yung column 11, this one, is the moments of inertia of the section with respect to the YY as the neutral axis. The next is the section modulus. Ito yon, yung 12. Section modulus of the section kapag ginamit siya ng nakahiga gaya nito. And of course, yung next column is for the radius of gyration. Sana guys naiintindihan. Ngayon ang tanong ay ganito. So paano natin ito gagamitin? Paano gagamitin itong ating pinakitang property in designing the most economical section? So balikan ko lamang itong discussion natin. Sabi dito, in selecting a structural section to be used as a beam, let us analyze the flexure formula. Balikan lamang natin yung flexure formula. Again, it is the flexure formula, di ba? That stress equals I, that moment is equal to the stress multiplied by I over C. Or simply, it is equal to the stress multiplied by the ratio of I over C. Diba? Ngayon, kung itong section na ito, yung ratio ng I over C will be substituted with S, natatawagin natin section modulus. Sa makatwid, itong ating moment will become equal to the product of the stress multiplied by the section modulus. Diba? And if we will compute for S, if we will compute for S, therefore S becomes equal to the ratio of the moment over the allowable stress. Ngayon, balikan ko lang, ipapaliwanag ko lang itong part nito. Ngayon, ano itong tinatawag ng S? Ito ngayon, yung tinatawag nating required section modulus, yung kinakailangang section modulus para masuportahan yung bending moment na M kapag ang kanyang allowable stress ay ito. Di ba? Ibig sabihin, ito yung kanyang kinakailangang section modulus. Diba? Nakita natin kanina sa table, meron tayong mga available section modulus for each of these section. Ngayon, anong gagawin natin dito? Sa makatwid, itong relation na ito na ipinakita natin, it will suggest that for the beam, that the beam must have a section modulus, yung I over C, that will be greater than this ratio of M over the allowable stress. In other words, yung allowable, yung available section modulus base do sa property ng cross-section ng beam, which is the ratio of I over C, ay dapat mas malaki doon sa section modulus required as the ratio of the moment to the allowable stress. Diba? Para hindi masira yung beam na gagamitin natin. Diba? Sa makatwid, kinakailangan nating maghanap ng section modulus that will be greater than the required section modulus of the beam. At para mas lalo nating maintindihan yung paggamit, yung interpretation to at yung paggamit, magbigay tayo ng isang halimbawa. I have here an example. Sabi dito, for the beam that is loaded as shown in the figure, and here is the figure. I will show the figure. Determine the lightest W shape that can be used if the allowable stress is 120 megapascal. Note that the weight of the beam is not yet included in these beams, in the loads that are indicated in the problem. So in the given, meron tayong allowable stress na 120 megapascal. Ito yung maximum permissible stress that the beam may be subjected. And the beam will be carrying this kind of loads. Ba? And we are asked to determine what would be the lightest W shape. Lightest, para masabi natin most economical. Kasi kung lightest siya, mas mura siyang mabibili. Di ba? So, how are we going to solve for the problem? Siguro ganitong una natin gawin, ano? Una natin gawin, solve muna natin yung reaction kasi kinakailangan natin makuha what would be the bending moment that this load will induce on the beam. Ano ba yung bending moment na mapuproduce nitong system of loads on the beam? Ano? So, we have to therefore solve for the reaction at the support. Yung very normal na procedure, we sum up moment about one particular position so that the reaction at the other point can be solved. And in this particular case, we can solve for the moment at B in order for us to solve for D. So when we have the moment at B equal to 0, we consider one direction as positive. Therefore, from here, we can solve for R sub 2. And what will be our moment equation if we will be taking moment here? Okay, our moment equation will be the following. Una, R sub 2 multiplied by 8 will be counterclockwise and therefore that would be positive. The moment due to this, 40 will be also positive. I will have plus 40 multiplied by 2. The moment due to this 50, 50 will be equal to 50 times 4 and that would be clockwise. Hence, that would have assigned negative considering that this will be our convention. And the moment due to this distributed load of a kilonewton per meter acting at the middle of the span. And so this will be equal to negative 12 multiplied by 8 multiplied by 4. At dapat yan ay equal sa 0. Kaya kapag ito sinimplify natin yan, we can solve for R sub 2 and R sub 2 will be equal to 63. Kaya itong R sub 2 natin ito yung 63. Diba? Ngayon, pagkatapos we solve naman our R sub 1 by summing up moment about D equal to 0. So, when we sum up moment about D equal to 0, again, if we will use the same convention as positive, assume natin na yung kanyang counterclockwise ay positive, we shall be able to solve for R sub 1. At ano yung ating moment equation dito? Unahin natin yung moment ng 40. This will be 40 will be creating a counterclockwise moment sa makatwid yan ay positive. The moment due to this 50, ito parang 50 naman, ano? Yung 50 naman will also create positive bending moment and this will be 50 multiplied by 4. Yung moment due to this 12 kilonewton per meter load will be 12 multiplied by 8 multiplied by the moment arm of 4. Okay, minus the moment due to this R sub 1, will be equal to 0. Dapat 0 yan. Kaya pag sinimplify natin ito, we shall be able to solve for R sub 1 at R sub 1 natin will be 123. Itong part na ito ay 123. Kaya pagkatapos nating ma-solve yung ating reaction at the support, pwede nating ma-solve yung maximum bending moment either by using the shear and moment diagram. Ano? Para masanay tayo, gamitin natin yung very basic procedure approach and we use the shear and moment diagram. So, when we draw the shear and moment diagram, subukan natin na i-drawing natin yung shear and moment diagram. At dito, meron tayong dalawang option. Ano? Una, papakita ko muna yung dalawang option, ay yung unang option. Kasi, mas maganda kasi kapag tayo nagsosolve ng problem, ay alam natin yung mga different options or different technique or approaches in solving. At from the solutions, ma-define natin ano ba yung mas advantageous in solving the problem. So, yung unang approach na gagamitin ko dito, yung unang basic, yung basic approach that is drawing the shear and moment diagrams in solving for the maximum moment. Diba? So, pakita natin yan. Ano? So, drawing ko muna yung kanyang moment diagram. Kunin ko yung mga controlling points. And then from here, i-drawing natin yung kanyang shear diagram. Okay, here, this is our point A, point B, point C, at point D. So, start tayo, no? So, we expect that at point A, K will be 0. I will not present here any more computation. I will just show how this point can be drawn using the relationship, diba? From A, 0. okay, ibabawas ko itong 40. So I will have negative 40. And definitely, it will be moving downward. Di ba? Walang load dito, so it will be horizontal. Mananatili itong 40. Di ba? And then, from 40, idaragdag ko itong 180 kasi upward siya, di ba? So, ano mangyayari? 40 plus 123 will be 83. Okay, 83 ito, di ba? At yung kanyang, connecting line will be vertical kasi ito ay vertical load. So, it will be vertical. Ayun. Di ba? From 83 hanggang sa C, mababawas siya ng total area. Itong area nito. Yan. Area ng uniformly distributed load of 12 multiplied by 4. And that is actually 48. Kaya from 83, ibawas ko yung 48. Anong matitira dito? 35. And how will this be connected? This will be connected by a straight line kasi ito ay horizontal. Straight line yan. Di ba? Then from 35, ibabawas ko itong 50. Ano matitira? Okay, nagiging negative 15. And how will this be connected? May vertical load, vertical line dito. Diba? Then from 15, ibawas ko ulit itong part nito. That is 12 multiplied by 4. And that's 48. So magiging negative, actually this must be negative, negative 50, negative 63. Diba? And this will be connected with a straight line. And then from 63, dagdag ko itong reaction na 63 din. So mangyayari 0 siya. And it will close therefore at 0 by that vertical line. So yan yung ating shear diagram. And then after we have computed for the shear diagram, masolve na natin yung moment diagram. So yung moment diagram, drawing ko dito, it is our moment diagram. Again, we have the points A, point B, point C, at point D. Mapansin natin, yung shear diagram crosses at B and C, which actually are a point where there are concentrated load. Ito mamaya, bibigyan ko na explanation, kung paano ko sinabi there will be two options. Okay? So for the meantime, ituloy muna natin yung ating illustration. So how do we get how do we draw the moment diagram? We start at 0, di ba? And then from 0, ibawas natin itong area nito. Di ba? Kaya ang mangyayari, I will have 40 multiplied by 2, and that is below the x-axis negative. I have negative 80 here. Diba? So from negative 80, idagdag ko itong area nito. I'm sorry, i-connect natin siya by vertical line. Then, idagdag natin itong area nito. Diba? Yun. Dagdag natin area na yan. So, anong mangyayari? I will have negative 80 plus this area. And that gives us a value of 156. And how will this be connected? How will this be connected? Okay, tingnan natin. The load here is downward. So, in my previous discussion, malalaman natin na ang moment diagram will be concave downward for a load that is directed downward. Kaya yung ating concavity dito will be in the downward direction. Diba? Ngayon, how are we going to solve for the moment at D? Now, if we will be subtracting from 156, this area, itong area na ito, diba? Anong mangyayari? So, you will go back at 0. Diba? And how will these 2 points will be connected? Again, this is a downward direction of the uniformly distributed force. Hence, yung kanyang moment diagram will be concave in the downward direction also. Ito yung kanyang concavity. And that gives us now the maximum, the moment diagram, having the maximum negative bending moment at negative 80 and a maximum positive bending moment at 156. Sa makatwid, yung ating magiging design moment will be at 156 kilonewton per meter. So take note that yung ipinakita ko sa inyo, yung option 1, that is getting the maximum moment using the shear and moment diagram. Ito tanong lang gaano katagal ba nating sunod yan? Medyo matagal-tagal din, di ba? Kasi we have to draw the shear diagram and then from the shear diagram, saka lamang natin na drawing itong moment diagram. Ngayon, ano yung option na tinutukoy ko? I have here the second option. Yung second option na sinasabi ko, we can define for the location of the maximum bending moment by inspection. And then we use the definition of the bending moment. So, we need to understand kasi dapat naiintindihan natin yung mga underlying concept in the relationship between the load, the shear, and the moment diagram. Ano ba isa sa mga underlying concept mayroon na na-discover nyo na? Sana na-discover nyo na yun. At ito yung sinasabi ko sa inyong underlying concept. Ito, I will show you here. Sabi dito, for beams that is subjected to concentrated loads. Okay, may mga concentrated loads tayo, no? The maximum moment normally occurs under one of the concentrated load. Ito yung dapat na nakuha agad natin nung mag-drawing tayo ng mga shear and moment diagrams. So, ang sabi dito, kapag meron daw tayong beams that are subjected to concentrated loads, kalimitan, ang maximum bending moment ay matatagpuan sa ilalim na kung saan naandoon ang concentrated loads. Diba? Ngayon, kung titignan natin dito, okay, itong ating loading diagram, meron tayong concentrated loads, okay, at meron tayo dito sa 40, sa dulo, A and D, at meron tayo sa gitna, sa support, at dito somewhere here, which is 50. Diba? So, kaya, asahan natin na yung maximum bending moment will either occur under B or under C. At yan ay nakita nga natin because the shear crosses the diagram at B and at C. And hence, we expect na yung maximum bending moment will be at B and at C. Di lamang natin alam kung alin ba sa dalawa ang negative at positive. At base dun sa ating computation, it is positive at C. Ngayon, paano ito gagamitin? Okay. So, in order for the given moment, okay, in order for us to solve for the given moment, okay, we will expect therefore that the moment will occur under the reaction at B or under the 50 kilonewton load. So, mga katuwid, kung gagamitan natin siya ng principle o yung definition ng bending moment, sabi yan, we're going to use the definition of the bending moment that is defined as the moment at B or at any point in the beam is equal to the summation of the moment taken on the left part of that exploratory section passed through B or taken on the right part of that exploratory section passed through the same point B. Diba? So that kung pag-aaralan natin ang kanyang convention dapat, those moment that would cause the beam to concave upward will be positive. Hence, kapag in-isolate natin yung left part, itong ating section, di ba? At kinuha natin yung moment dito, di ba? Moment dito. So we'll be getting the moment at B. And what are those moments that can be taken by definition? Okay, by definition, the moment at B will be equal to 40 multiplied by the moment arm, and that is equal to 40 multiplied by 2 and gives us negative 80. Why negative? Kasi kapag nag-take tayo ng moment dito, the 40 will tend to concave this part of the beam in the downward direction. Hence, it will be signed as negative. Diba? Kaya meron tayo ditong negative 80 kilonewton per meter, and that is equivalent to this magnitude. Samantalang yung second part naman, okay, puntahan natin yung second part. Sabi dito, yung moment at C, ito ng part nito, will be also taken as the summation of moment taken on the left or on the right part of that exploratory section passed through C. Diba? Kaya kung ginamit natin yung right part of that exploratory section, ipass natin yung exploratory section. Okay? So, kuha tayo ng section dito and then we take the right part. So, this moment will be our moment at C. And this moment can be taken if we sum up the moment caused by all of these loads acting through C. And these are the following. Makikita natin that this will be equal to 63 multiplied by 4. And what would be the moment at the sign? Now, kung pag-aaral natin, ang epekto nitong 63 dito sa section na ito, okay, will be causing it to concave in the upward direction. Hence, it will be signed as positive. While the moment due to this uniformly distributed load having a magnitude of 12 multiplied by 4 multiplied by 2 is equal to negative because it will be causing a downward direction. Hence, the magnitude of the same moment will be 156 kilonewton meter at ito rin siya yung maximum moment na nakita natin dito. Kaya, nasa inyo na yung kung ano yung magiging approach ninyo in solving for the moment. Either you use the definition or you use the relationship between the load, the shear, and the moment diagram by the use of the shear and moment diagram. Di ba? So, balikan ko lamang ito, part na ito. Ngayon, pagkatapos natin makuha yung maximum bending moment, what shall we do? Okay, pagkatapos natin makuha yung maximum bending moment, what shall we do? Now, we are now ready to solve for the required section modulus. Makukuha natin yung required section modulus, di ba? Ano ba yung required section modulus? Yung required section modulus will be equal to the ratio of the maximum bending moment and the allowable stress. And we have computed the maximum bending moment at 156 times 10 to the 6th. This becomes now Newton millimeter. If we will be dividing it by the allowable stress, this gives us a value of 1,300 times 10 cube, or 130,0000. This unit will be millimeter cube. Ang kanyang unit will be millimeter cube. Kaya that is equivalent to 1,300 times 10 cube of millimeter cube. Take note, ito yung required, kailangang section modulus para masuportahan yung loads nung beam. Di ba? Ngayon, what shall we do? Now, we will be now looking for any available W shape from the table, having a section modulus just above the required S. Mamimili ngayon tayo ng mga available W shape na mayroong section modulus na equivalent or mas mataas ng konti dito. Kasi pag kumuha ka ng mas mataas na mas mataas na higit na mas marami, mabigat 'yon. Hindi siya economical, di ba? So kinakailangan ito yung ating magiging basihan. At magsimula tayo do sa pinakamaliit na section muna. So I will show you here the lowest. Ito yung mga section na matatagpuan natin, no? Ang makikita natin pinakamaliit na section is W130 by 24. Ito yung pinakamaliit na available in the industry. Diba? At ito yung section na hinahanapan natin kay column 1, 2, 3, 4, 5, 6, 7, 8, column 8, where you will be looking for the S. So, dito tayo mag-start. Hanap ngayon tayo ng section modulus that is just greater than 1,300. And you can find that somewhere here, wala tayong nakikita. Only the maximum at this section is 31.4. So we move to the next higher group. Yung higher group natin will be found at, ito naman yung group 200 and 250. Medyo tumataas ngayon yung ating depth ng beam. At on that section, ito yung kanyang mga available section modulus. And you can find somewhere here, yung next, yung pinaka-lapit. Nakita niyo itong 1,400. I will mark this part. Yan, 1,410. This 1,410 is a section modulus just above 1,300. And this section modulus is for the section W250 by 115. Ibig sabihin, meron tayong depth na 250 at ang kanyang approximate mass is 115. Kaya pwede natin siya i-consider as one of our choice in our selection. So meron tayong designation dito, yung kanyang available section modulus at yung kanyang mass, kasi mamimili tayo ngayon kung ano yung kanyang mass na gagamitin natin. So yung available na nakikita natin so far is 250 by 115. Ito yan. Ang kanyang section modulus is 1410 at ang kanyang theoretical mass is 114.8. Diba? Pero hindi tayo titigil diyan kasi it is just one of the available section modulus. Next, puntahan natin yung next higher group. So 250 tayo, punta tayo sa next group. Nasa 310 tayo. Okay? So, sa 310 dito, di ba? Punta tayo dito sa part nito at matatagpuan natin. Meron tayong eksakto, no? Eksakto na 1,300 dito. Kaya lang itong eksakto, binanggit sa problem kanina, di ba? Binanggit sa problem na yung weight of the beam is not yet included in the load. Sa makatuwid, kung gagamit tayo ng eksakto, tandaan natin, yung weight ng beam ay madadagdag din sa kanyang bibit-bitin. Sa makatuwid, inaasahan natin na yung required section modulus ay higit na mas malaki sa 1,300 kasi nga meron pang weight yung beam na bibit-bitin na kanyang sarili. Di ba? So, yung weight ng beam will also add kay certain amount of section modulus required. Kaya itong kay 1,300 dito, definitely ikasisira agad masisira din yung ating material. Kaya hindi natin dapat i-consider. So, ang next higher value is 1,480 itong part nito. Yun, 1,480, di ba? At ang kanyang section is W310 by 454. Okay, so kunin natin siya. Ang kanyang available na section modulus is 1480 at ang kanyang theoretical mass is 454. Ito yung 454. Di ba? Meron tayong dalawang napipili dito. So, stop na ba tayo? Hindi pa, kasi ang pinapahanap sa atin, lightest. Hindi tayo sigurado kung ito na yung 114 yung lightest, di ba? Bagamat kung ikukumpara, ang laki ng isa, 454, kumpara doon sa 114. Pero, puntahan natin yung next group. Nasa 310 tayo, punta tayo sa mas mataas, 360 ngayon. Ito yung depth, 360. Okay? So, puntahan natin itong S na ito. And we have here, 1280, hindi pwede ito. So, next is 1510. Ito yung available na pwede natin kunin. 1510. And this will be for W360 by 91. Diba? Then, this is also has a available of section module 1510. And an approximate theoretical mass of 90.8 okay, kilogram per meter. Okay? Next tayo, punta tayo sa next higher group. 360 baka sa mas mataas na section na mas malaking section ay meron tayong makita. 360 pa rin to, di ba? So automatic 360. Ito yung kinuha natin kanina 141 360. Okay, wala na tayo. Okay. So next higher group is 410. Ito 410. Ang makikita natin available is 1,330. Kunin natin itong section na ito na W410 by 74. Ng kanyang available section modulus is 1,330 at ang kanyang approximate weight is 74.9. Diba? At mapapansin natin, okay, sa next higher group, baka meron pa sa mas malaki. Puntahan natin yung mas malaki. 460 tayo ngayon. Diba? 410, 460. Itong palaki. Ang available is this one, 1,320. Diba? So, kunin natin itong 1,320. Puntahan ko, balikan ko lang. Okay, balikan ko lang. Yung 1,320, maaring ito ay hindi natin isama kasi nga meron lamang tayo ditong available na okay, sabihin natin factor of safety of 20. Eh dahil may weight siya, baka due to the weight ay mag-exceed siya doon sa kanyang required section modulus. Kaya ang kukunin ko ngayon dito is 1,460 na sa section na 460 by 74. Kaya kunin ko itong part na ito. Okay, so I will have 460 by 74. Ang kanyang available is 1,460 at kanyang weight is 74.2. And then in the next group, meron tayo dito. Okay, ito yun. Next group is 1,340. Diba? And this will be for W530 by 66. Ayun. Kanyang available is 1,340 at 65.7. Okay? So, meron pa ba sa pinakamalaki? Ang pinakamalaki niyan is actually 1 meter halos. Baka meron pa. Sa 610, 1,008 na yung kanyang pinakamaliit. So, wala na tayong masyado na mabigat ito. Diba? Okay, meron tayo ditong 3,500 or 690, 44, and then, ibig sabihin, wala na tayong makita mas malaki pa. Okay? Mas maliit lang, mas lighter. So, ito lang yung available. Ngayon, pagkatapos natin makita yung available, mamimili tayo alin sa mga napili natin na may pinakamagaan. And you will find that this one is the lightest. Diba? 65.4 followed by 74.2. Kaya lamang, kaya hindi tayo tiyak na itong 65.4 ang ating gagamitin, W520 by 66. Kasi ang kanyang available section modulus is just 1,340. Take note, ang hinahanap natin kailangan ay 1,300. Yung bagang 40 na kasobrahan nito ay sapat para suportahan yung kanyang weight. Kung sapat, then we will be using this as the lightest. Pero kung hindi, mamimili ulit tayo. Yung next naman, next lighter. Okay. And the next lighter is 74.2, offering ay 1,460 section modulus. Di ba? So, what shall we do next? We need to test for the actual section modulus required kapag isinama na natin itong weight na okay, 66 kilogram per linear meter. So what shall we do? Okay, puntahan natin. Okay, ang gagawin natin is we try to add the weight of the beam and solve for the required section modulus that will be caused by the moment due to its own weight. Diba? Kukunin natin yung section modulus, okay, na required kapag isinama na natin itong weight ng beam. So instead of drawing, computing back the total moment, so ang gagawin ko na lamang siguro dito ay idaragdag ko na lamang yung weight at yung weight ay i-analyze ko separately. Diba? Sabihin, ito lang yung gagawin ko. Kinuha ko lamang yung weight. Diba? So, ibig sabihin, wala na yung load ko. Ang ina-analyze ko na lamang dito ay yung weight. Na kung saan yung weight ay 65.7. So, I multiply it by the factor para ang maging unit ko is 0.644517 kilonewton per meter. So, ibig sabihin, I need to determine the resulting moment due to this weight of the beam of 0.644517 kilonewton per meter. Ngayon, saan natin matatagpuan yung maximum bending moment due to the loading? Yung loading condition ay nag-cause ng bending moment at point C. So, inaasahan natin, dahil sa liit nitong 0.644517, hindi makaka-apekto itong weight na ito sa position ng maximum bending moment. So, asahan natin na yung maximum bending moment ay naroon din sa C. Kaya kukunin natin ngayon yung moment produced by this at point C. And this can be taken by getting first for the resulting reaction at R sub 2. Diba? R sub 2 due to the weight only of the beam. And this will be equal to 65.7 times 0.00981 times 10, representing the weight, times 4, representing the moment arm, divided by 8, representing the span. Okay, the moment arm of R sub 2 from this point B. And so from here, masolve natin yung R sub 2 to be 3.22585. Yung part nito, yung reaction dito. Pagkatapos, solve natin yung additional moment at C due to the weight. And this will be taken as 3.22585 multiplied by 4. If that will be taken if we will be summing up moment about C, diba? And we consider the left hand side of the exploratory section. I'm sorry, the right hand side of the exploratory section. Kaya we shall have here 3.22585 times 4, representing the moment arm of R sub 2 prime at point C, minus yung moment due to the weight, that is 0.66517 times 4 times 2. And so here, you shall have the moment of 7.7 kilonewton meter. Ito yung moment na na-induce ng sarili niyang weight at point C. At sa makatuwid, dapat natin itong i-add doon sa 156. Di ba? Kaya yung kanyang magiging total moment will be 156 plus 7.7. O kaya naman, pwede natin kunin yung additional section modulus nitong moment na ito kapag ito i-divide natin sa allowable stress ng material. And so we can solve for the additional section modulus due to the additional moment at C. And that will be equal to 7,700 times 10 cube. This becomes millimeter cube divided by 120, and that gives us 64.651. Sa makatwid, ang total S required pag pinagsama na itong loading at saka yung weight ng beam will be 1,300 plus 64, and that gives us 1,364. At tingnan ulit natin ano ba yung ino-offer nitong section nito. It is only offering 1,340, which is less than the total required, di ba? Ito sabi dito, since the total required section modulus is 1,300 plus 64.451 is greater than what is being supplied from this section, which is just only 1,340. Sa makatwid, if we shall be using W520 by 66, it will fail because it will have lesser section modulus. So, hindi natin pwedeng gamitin itong W200 520 by 66. Ano gagamitin natin? So, we will be selecting the next a lighter section, which will be W460 by 74, offering a section modulus of 1,460. Maring tanong, sir, do we have to check again the weight of the beam? Siguro hindi na kasi ang resulting section modulus required lang is only 64. Kung madagdagan man siya ng 11, tingnan 9 kilogram per linear meter, hindi naman siguro aabot ng 100 yung additional section modulus na idaragdag mula dun sa additional difference ng dalawang section. Di ba? Kaya sa pamamagitan itong ating discussion na pinakita ko sa inyo ngayon, sana guys ay naintindihan ninyo itong application, kung paano gamitin ang section modulus, particularly in the determination of the most economical section. Once again, thank you very much for watching.